All right, so here we're doing 2.5 uniform circular motion. Uniform is just another way to say constant. Okay, so this can be anything going in that circular motion. That could be a moon or satellite going around Earth. That could be a planet going around a star. That could be you simply have a yo-yo with a string or a bucket of water that you are spinning around. Uniform circular motion. Okay, constant speed. So you are rotating that around at a constant speed. We'll talk about a little bit more about that on that next slide. So when we have this little picture here, we see our velocity and our acceleration. If I was showing that velocity at another point, it would still show as a tangent with the acceleration heading into the center. If the velocity is at the bottom, it is again showing tangent with the acceleration into the center, and it just goes around like that continuously. So the velocity is always going to be tangent to the motion, so that's a little bit different than otherwise. The acceleration is always going to be towards the center, and so that's going to create some different items here that we'll talk about in a second. Okay. Key terms: a period is the time of one revolution, and it's shown by a capital T. Okay. You're probably not going to need to use omegas, which is the radial velocity or radians per second. Most of the time, you're going to be using this equation down here to find your velocity. 2 pi r over the period equals your velocity. Okay. What other things could they give you? They could also give you the frequency, which is the inverse of velocity, or of the period. So frequency is equal to 1 over big T, just like big T is going to equal 1 over frequency. So you could add those information there. Same thing that we talked about before. Velocity is always changing because we saw it on those 4 different points, but you could really do 360 different points, all tangent. Okay. Its magnitude is the same. Its units are the same because that is the speed portion of velocity. But velocity is speed in a certain direction. When we look at over here, we see we're going to have different directions. So we have different velocities because the direction is always changing. So we can have constant speed, but changing velocity. If I have changing velocity, what else did we notice? The acceleration is changing. It's still acting towards the center, but it is a different amount because of that direction again. So velocity is perpendicular to the acceleration. Velocity is tangent to the path. Velocity is changing. So even if you have constant speed, you are still going to have changing acceleration. And that brings us to our next equation. Okay, write it down both ways, but primarily what you're going to be using is v squared over r. So a totally different one. This only works for circular motion. Don't try to apply it any other place. There's a bunch of practice. Here are the hints for the practice. So especially if you get items wrong on your first attempt on the quiz, come back and do this. If you want to work steadily through, yes, do the application first so that you have that really good, strong foundation skills before you move on. Just remember there's some hints here in the video if you need them, because those are things we have not gone over with. Okay, so Jill spun the 1.0 kilogram pail. And we want to always, when we're doing these, write down our givens and our knowns. My givens, I circle, and my unknowns, I underline so that I can convert from a word problem into whatever equation I need. So Jill spun the 1.0 kilogram pail. Kilograms are a unit of mass in a circle, so I know I can use the circular motion equations with a radius of 1.1 meters. So that's obviously the radius, and made 1 turn every 3 seconds. So then I got to go back. Is that a frequency? Is that a period? Period is one turn, the seconds it takes for one turn, or the time it takes for one turn, and then convert it to seconds. So that is my period because it is talking about one turn is a period. And what are we looking for? Meters per second speed. So that's us looking for that velocity there. So what's my equation for velocity? V squared equals 2 pi r over t. Do I know my radius? Yep, 1.1. Do I know my period? Yes, 3. Plug it in there. When you do this, use the pi in the calculator. Do not use 3.14. It's not accurate enough for some items. And then report to 2 decimal places, just like always. So you would get an answer of 2.30 meters per second. Okay, again, we assumed air resistance is 0, so that is why we did not use the mass in this case. Okay. Pluto goes 37,000 meters per second. Well, there's our speed right there. So when we circle, we're going to circle that as our velocity. It takes 248 years. So that is our period. If they do not want your period in years and they want it in seconds, make sure you would convert to seconds. Now, we're not necessarily going to need it for each problem. Just be aware that if they want you to use it in an equation, it needs to be in seconds. Okay. The path is 19,640 kilometers. Path, that's what it actually travels. That's why it's the circumference. And our circumference is 2 pi r. Okay. So what are we trying to find? Acceleration. What is the acceleration equation? V squared over r. Do we know a V squared? We do, 37,000 meters per second. Do we know a radius? No, read carefully. Don't just assume if they give you a unit of length, it is a radius. It's not, it's a circumference. So we're going to have to calculate our radius. 19,640 kilometers is equal to 2 pi r. Now, if I leave it like this, what units is my radius going to be in? It's going to be in kilometers. Can it be in kilometers for here? No, because acceleration is meters per second squared. So everything has to be in meters or seconds. So make sure you convert from kilometers to meters and then put it in your circumference equation. And you're going to get that for your radius. And now I can finally plug 3,125,803.08 meters. That can now be plugged in there to get us an acceleration. So it's a really, really, really tiny acceleration. Sometimes you don't expect that. That's why it's important to make sure you do each problem all the way out and watch your units. A couple little key terms here. Synchronous orbit. Geo just means Earth. Synchronous just means same. So when you are looking at it, you've probably heard about satellites. So I have a satellite up here, and it's often in spy movies. Well, our satellite's not coming into place because that satellite only covers a little area of land based on the cone that it's able to give from space. And so as it travels around the Earth, it's traveling at a different rate than the Earth is rotating. Okay? So you have to wait for the satellite to come into the next place. Well, geosynchronous orbit means that the satellite or whatever it is stays over the same land. So it's the satellite is our area and it's our cell tower one and it's staying over Virginia. This is not completely accurate in real life. I'm just trying to give you something that you can picture. So even 6 hours later, that same satellite is still over Virginia because it's going around so that it stays directly above that one. So that's what geosynchronous means when you hear about it in movies and stuff like that. So what could we have? We could have a question wants us to compare two satellites. Okay, so here we have our Earth one satellite is 500 meters above Earth. So here we go with one satellite. And another satellite is 750, but they are parallel to each other. So when we're talking about parallel, when we're talking about these big spaces, even though, yes, you could put parallel the other direction, when they're talking about it in these types of situations, is parallel while maintaining their entire path. So they would be directly over, so they're going to be showing the same kind of area. Okay. So that would be how we set up that first part of the equation. Two satellites stay consistently parallel to each other. They're not necessarily geosynchronous, so they could be or they could not be. The satellite further away has to travel faster. Why is that? Okay, so this 500 has a path that looks like this. And the 750 has a larger path. And yes, my drawing is horrible, but larger path because this circumference is larger. Okay. If I had to straighten those out, the blue would be much further than the green. So if they're going to stay parallel with each other, then the green maybe had to travel a shorter amount, or not maybe, definitely travels a shorter amount than the blue. So for them to stay at the same spot, that blue person has to go faster. So the one with the larger path has to go faster. Okay. Now, if we wanted to compare the accelerations, where are the accelerations always going? Towards the center. Accelerations are always going towards the center. So that is the direction of the acceleration of both of those satellites because they're staying parallel. But how can we compare other information? Okay. So that first satellite has the radius of the Earth plus 500. And that second satellite had the radius of the Earth plus 700. So the radiuses are different. We've already talked about the velocity of the larger path. What about the acceleration? These guys are directly proportional, Okay, so 2 times the angular velocity means that you had 2 times the radius. So you can set up a proportion there to compare those items. And there you go with 2.5.